we have built here a very nice topology of many vendors. You see the logos that participated into this demo of how to use SR MPLS as a base for the 5G xHaul design. So the goal of the testing is to verify that we can interop. That's why EANTC is called like this. We can interop between all of the vendors, and we can build ORAN on top of SR MPLS. So we need to connect ORU, ODU, and OCU. Sounds very simple, but it's not that simple if we look into details. So we need to effectively handle all of the three types of communication: fronthaul, midhaul, and backhaul, with certain parameters that are compliant to the working group 9 of ORAN. So the elements that we've been focusing on during the testing in Berlin a few weeks back is first the clock synchronization profile, which is G8275.1. And we made sure that all of the clocking packets are being sent into the high priority queue. Because if you lose clocking in ORAN, that's not good for the ORAN itself, for the network. Then we, of course, have traffic, which is digitalized signal from the radio units towards the use. And we need to understand what type of traffic is being sent. Some ORAN providers, they mix both the radio signal and customer traffic or business traffic over the same infrastructure. So we need to make sure that we classify the important low latency packets as such, and classification needs to be done on all possible layers. So we need to classify L3VPN, for example, with DSCP bits, Ethernet priority for Ethernet-based enhanced CPRI traffic, and MPLS experimental bits if you are a device somewhere behind in the middle. Then, of course, we applied the time synchronization to the network, and we have put to ourselves a budget to stay within 100 microseconds altogether end-to-end. The topology is really exhaustive, and the three main layers are listed. So we have access devices, ORUs, and you see the names who participated into this topology. And then we have pre-aggregation layer that connect those ORU devices together. And then we have aggregation and core devices, the two on top. And those two on top are connected to Grandmaster. So clocking is really important into ORAN, and we made sure that we can use our network as a source for the clocking. So not every device had their own, connection to clock, but they were all synchronized from Grandmaster downwards. And with this, we need to switch to the explanation how this clocking is working. And for this, I will give the word to the expert, Victor.
Good afternoon, ladies and gentlemen. Here is the drawing of this test setup. We use synchronization G8075.1 profile as a PTP, and also we use SYNKey. As usually, SYNKey is used for frequency synchronization, and G8275.1 PTP is used for phase and optionally for time synchronization. And we have two nodes, Nokia and Juniper Class D devices connected to Grandmaster. They are configured as boundary clock. So that means that they are synchronized from Grandmaster and then resent the sync messages down to hierarchy. The next level is Ciena and Arrcus nodes. They, of course, configured in the same way as a boundary clock. And then all list of vendor nodes like Nokia, Juniper, Arista, Ericsson, Arrcus, Keysight, Ciena, H3C, and Huawei, who participated in this test, there are the nodes as a PE device connected to ORU in 5G network. Please, next slide. Okay, so next crucial part for this, this is QoS settings. that's what my colleagues Anton already mentioned earlier. So we have configured Ethernet classification for .1p. 0 is low priority traffic, 6 is high priority traffic. IP, we have DSCP values CS0, CS6. And SR MPLS, traffic class 0 and traffic class 6 for low priority traffic and high priority traffic. Then, of course, what we could expect that all these three classification, any traffic on any layer, either Ethernet or IP or SR MPLS, the low priority traffic would experience some random discards in case of overload on the link, but high priority traffic should not be affected. So that means no traffic loss, and the latency delay is under 100 microsecond budget. For this demo, we want to demonstrate just a connection between one pair of devices. So in this case, it will be Arista or connected to ORU and Huawei connected to ORU. But earlier in Berlin, we checked all vendor to vendor, any vendor to any vendor for such QoS and synchronization. Okay, next slide, please. Okay, and what in this test procedure, we provide network-wide time synchronization with this G8275.1 profile and sync E. We're gonna send the multiple best effort, low latency flows, and priority flow for traffic on 5G xHaul network. And as a result, we could see that synchronization is not affected by oversubscription, and one-way latency ECPRI streams is kept in the budget of 100 microseconds. And here is the live demo. I will start with Nokia device facing the Grandmaster. So here is the configured sync if timing. We could see here that we use the port from microchip Grandmaster clock, and it's locked for sync E synchronization. We could check the PTP. So for PTP, you can see that time priorities like time scale, frequency traceable, etc. And we could see all the other parameters that we receive for PTP time recovery. Also, on the next example, we're gonna see that on the port for PTP, this port is slave to Grandmaster, to microchip, and the next port to Arrcus is the master port, so it will resend the PTP messages and keep the lower hierarchy synchronized. Okay, that's it, and I'm gonna give the stage to other presentator.
All right. Thank you, Victor. All right, so I think let's go back to the topology one. So as we mentioned the test procedure, we're sending two types of traffic. One is essentially your best effort, which is L3VPN, and the other is high priority traffic. So the traffic pattern we have going right now is basically the ORU layer, all the way to the ODU layer and back to the ORU. The traffic is simulated by Keysight. The first hop is the Arrcus, and it hits the Ciena device here, cross connects to Arrcus again, and goes back to Huawei device here. So we look at the ingress P or the access layer to see how the traffic statistics look like. So going back to the device, this is the Arrcus access. I have a small cheat sheet to make it easier. So this is the incoming interface. You know, this is the address that the traffic will be hitting in, which is part of an L3VPN VRF. As you can see, the bond interface is part of the L3VPN VRF here. We'll just look at the destination prefix for the traffic is going in. So as you can see, the Destination prefix is reachable through a VRF, and this is the service label or the L3VPN label for the remote. So this is basically demonstrating your best effort or your business traffic. And to reach this particular next hop, you would actually have a transport label, which is an SR MPLS label. So it's a dual stack packet that leaves the access device. So this represents your best effort traffic. And at the same time, we shall see what is going on with the uplink interface, where we have both the best effort and the high priority traffic coming in. So I have this interface, which is part of the uplink. We actually have a shaper configured or a policer configured here, which is going to prioritize your high priority traffic. And then we can easily look to see what the QoS policy looks like. So essentially, it's taking all the traffic that's part of traffic class 6 and putting it into a low latency queue, so that it does not get dropped no matter what. We'll see the statistics quickly here to see how that gets represented. So this is the overall statistics on that interface. If you watch closely here, the classifier for the traffic class 6, which is high priority, the drop counts and the drop bytes are all 0, which means the high priority traffic is not dropped whatsoever. So that means your ORAN architecture is kept intact, while you also see the queue drops happening for the best effort traffic. So the end goal here is basically to demonstrate and show you guys that no matter if there's any congestion, there is end-to-end priority traffic that's reaching all the way to the ODU layer. We'll also look at some of the clock statistics in here to kind of see. If you look at it, the clocks are logged both on the sync key and PTP, which we can showcase using the graphs that we see on the Keysight. Overall, you see the clocks being logged and the clock being delivered. With that, I'll hand it over to Santan from Keysight to kind of showcase the lakes here. So overall, at the end, if you look at it, the end-to-end topology, you have traffic going from one access P to the other, which is best effort, while you're protecting your high priority queues.
Thank you, Aditya. So I'm going to show two types of measurement. One is the first one is the traffic measurement, and second one is the timing measurement. So if you remember, so we have 9 access devices, and out of 9, we have configured traffic for 2. So basically, we have Arrcus, and then we have Huawei with these 2 access routers. We have 2 hosts attached, and we have configured 2 types of bidirectional flow. One is high priority, another is best effort. And if we look at the statistics here, so you can see the first 2 rows are showing 0 loss. So these are basically high priority 1. And the last 2 are showing around 15% loss. By the way, so the total throughput of these traffics are enough to congest the link, and we can see that at the event of congestion, best effort traffic is getting dropped. So that's on the loss. Now let us look at the latency. So here in latency, if we look at this row here, for the first 2 rows, you would see around 60 microsecond of latency, which is basically 4 hops and also some latency coming from a harness switch. So probably we should exclude 2 microsecond out of it, and we can say that with 4 hops it's actually going to be 40 to 50 microsecond, not more than that. Whereas if we look at the last 2 rows, the latency numbers are much higher, because that's the best effort traffic that suffers. So that is on the traffic measurement. Now let me show you the timing measurement. So on the timing measurement, so if you remember, right, so we have basically 3 hops from Grandmaster, and here the time error is getting measured on the Arrcus, and we see around 70 nanosecond of time error traversing through 3 hops, which is really commendable. And then if we look at the sync key measurement on both Huawei as well as Arrcus, we could see it's the peak to peak is not even 1 nanosecond, and it tells us that sync key is working properly. And finally, we would take a look at relative time error between 2 access Ps, Huawei and Arrcus, which comes out to be 115 nanosecond. And considering it's actually 7 hop, because the only common point is the grandmaster. It really commendable, and it should serve whatever ORAN requires for maximum relative time error. With that, I want to conclude this presentation. Thank you.